Let's see an example of finding an area between curves. We want to find the area of the region bounded by or between the curves f of x equals x squared minus 2x plus 2 and g of x equals x plus 3. We need to know which curve is on top, though, and the only way I know of doing that is by sketching a graph. So let's do that. Here's a little review of graphing parabolas. First of all, I know this is going to be a parabola because the highest power on the x is an x squared. When the highest power is 2, we have a parabola. I'm going to start by finding out where the vertex of the parabola is. Oh, before that, though, let me point out that the coefficient on the x squared is positive. It's an invisible positive 1. And that tells me the parabola is going to be opening upwards, like that. If the coefficient on the x squared was negative, it would be opening downwards. Okay, now let's find the vertex. We'll use the vertex formula. Which is x equals minus b over 2a. A is the coefficient on the x squared, which we just said was a 1. And b is the coefficient on the x, which we can see is a negative 2. So our vertex is at x equals 1. What's the y-coordinate there? Well, to get that, we just plug the 1 in to the formula. So 1 squared minus 2 times 1 plus 2, which is 1. So there's our vertex, and it's going to be opening upwards from there. It can't have any x-intercepts because it can't touch the x-axis because its lowest point is at the vertex. But let's see where it crosses the y-axis. The y-intercept is always at x equals 0. So the y-intercept will be at f of 0, which is 0 squared minus 2 times 0 plus 2. So when you're figuring out the y-intercept, any term with an x gets wiped out by the 0, and you're left with just the constant term. So there's another dot on our parabola. And that's really good enough for us in this context. So we know our parabola looks something like that. For g of x, that's a linear function. That's going to be a straight line. I know that because there's no exponent on the x. I'm going to graph this by finding the x and y intercepts. For the x-intercept, y would be 0. So we'd have 0 equals x plus 3. So x would be negative 3. And for the y-intercept, x would be 0. And therefore y would have to be 3. So our line is going to go through the y-axis at 3 and through the x-axis at negative 3. Now we're told we want the region between x equals 0 and x equals 3. Three will be somewhere there, and so what we want is this area. Now we can set up our definite integral. So the area will be the definite integral from 0 to 3 of the curve on top, which in this case is called g of x, minus the curve below, which in this case is called f of x. Let's put the formulas in. G of x was that straight line, x plus 3, and f of x was the parabola, x squared minus 2x plus 2. Let's simplify the thing we're integrating. I'll start by distributing the minus sign into the parentheses. Then I'll combine like terms. Let's see, x plus 2x's is 3x, and 3 minus 2 is 1. So our antiderivative will be minus 1/3 x cubed plus 3/2 x squared plus x. And we're evaluating from 0 to 3. So plugging in the 3, we have minus 1/3 times 3 cubed plus 3/2 times 3 squared plus 3, and plugging in the 0, we have, well, minus 1/3 0 cubed is going to be 0, 3/2 0 squared is going to be 0, and plus a 0. In that first term, the 3 down below cancels one of the ones on top, so the first term simplifies to just -9, and then I have plus 27/2 plus 3 combining the -9 and the 3, we have -6, and I'm going to need a common denominator because of the fraction, so let's multiply that -6 by 2 over 2. So we have -12/2 plus 27/2, which is 15/2. So what we just determined is that the area of our green shaded region is 15/2.